All right, welcome back everybody. In this video, we are going to start Unit 2 of AP Calculus, Differentiation, the Definition, and Basic Derivative Rules, with Section 1, Defining Average and Instantaneous Rate of Change at a Point. I'm going to do 2 videos on this section, so here's the first one. We'll go ahead and get started. All right, it mentions right here in this lesson, we're going to discuss the concepts of average and instantaneous rates of change and look at the similarities between the two, as well as some differences. I'm going to start right off with an example. Example 1 here. Anna throws a softball up into the air, and the graph below shows the height of the ball in feet at various times, measured in seconds. What is the average rate of change of the height of the ball on the interval from 1 to 5? Don't forget to use the correct units in your measurement. Okay, so this is a concept that we've done several times before, I'm sure, in earlier courses, although maybe not necessarily in this context. But hopefully you know that the average rate of change of the height of a ball over a given amount of time is the change in height divided by the change in time. So we're going to identify the two heights, this height, the ending height on the interval and the starting height on the interval. It's a little hard to read these points here, but that's the ordered pair 5, 30 at the top. And over here to the left is the ordered pair 1, 14. So the change in height is going to be 30 minus 14. And the change in time is going to be 5 minus 1. And so we go ahead and calculate that. Gives us 16 over 4, or 4. And then we need our units. Height is measured in feet, so the numerator of this is in feet. The denominator is measured in seconds, and so our unit here is going to be feet per second, however you opt to write that. All right. So that's the average rate of change of the height of the ball. A little bit more information tied into that. What we saw here was we actually saw a secant line through these 2 points. We'll see if I can draw one on the first try. There we see a secant line through those 2 points, and I don't know if you remember the context of a secant from geometry. You probably looked at secants of circles, which were lines that intersected a circle at 2 points. Similar, kind of definition falls here for curves. Basically, the secant line is going to go through 2 points on our curve. It might go through more, but it's going to go through at least 2 points on the curve. And when we talk about things graphically, the average rate of change of the function is the slope of this secant line. And so that's a good way for us to define the average rate of change of a function. It's just the slope of a secant line through 2 points on a curve. Okay, that's the average rate of change. Now, the instantaneous rate of change is what we're going to find next. We're going to use this graph. I'm going to go to an animated version of this graph. What we're going to do is we're going to try and find the instantaneous rate of change of the height of the ball at time t equals 1. And again, we're going to use the correct units of measure. Now, the challenge here, when we were finding average rate of change, all we had to do was find the slope of the secant line through 2 points. And so if we wanted to find the average rate of change between these 2 points, for instance, we'd just find the slope of the secant line through those 2 points. And if we wanted to find the average rate of change between these 2 points, we'd just go ahead and find the slope of the secant line through those 2 points. But when we're trying to find instantaneous rate of change, we're trying to find the rate of change just at this one moment. And so we don't have 2 points to draw a secant line through. And so we've got to get a little bit creative in our approach to this. And that's what you're going to see in this example. We're going to look at this graph at just time 1 and figure out the slope of the tangent line to the curve at that point. And that's going to be our instantaneous rate of change. So let's go over to the sketch here. All right. So how are we going to find the instantaneous rate of change at one point? Well, we're going to start by looking at 2 points. And on this graph, I've started with the points 1, 14 and 6, 29. And I've drawn the line through those two. And something else that I've done over to the left here, this is where you want to really pay attention as we look at this sketch. I've set up the slope formula from the point 1 to whatever point, and I can move this point around here using my little slider. And you see, as I move that point around, you notice that the slope here changes. Okay, so what I want to do here in order to find the instantaneous rate of change is I'm going to look at the slope of that secant line, and I'm going to take this point 629 and I'm just gradually going to move it towards 1. And you see, when we get to that point 530, we get that slope of 4, which was our average rate of change from example 1. And I'm going to go ahead and keep sliding and watch the slope as this point gets closer and closer to 1. And you'll see it's growing and growing and growing, and we're getting where the points are closer and closer and closer and closer together. And when the points get on top of one another, the slope's undefined because the denominator is 0. But if you watch those last few moments beforehand, you see that this slope, it looks like it is approaching 8. Okay, so this ties in perfectly with the concept of the limit from unit 1. This point moves closer and closer and closer, and the limit of this value as one point approaches the other appears to be 8. That's going to be our instantaneous rate of change at time 1. It's going to be 8. And the units are still, just like for average rate of change, feet per second. Okay, let's look at these definitions and how they work. First form, and this ties into the way that I wrote it on the little Desmos sketch. If we're looking at the average rate of change, thin that up a little bit. The average rate of change, we're looking at the secant line that goes through these 2 points. The point A, f of A, and the point A plus H, f of A plus H. Okay, that's our average rate of change. All we've done right here is taken the slope formula, f of A plus H minus f of A, all over A plus H minus A, and we just simplified the denominator, and that gives us a formula that represents the average rate of change between these 2 points, A and A plus H, where H is just some arbitrary distance between the 2 points. It might be 2, it might be 5, it might be 0.1, whatever it is. It's just some distance between the starting point and the ending point. You should recognize this from pre-calculus. You should have been introduced to the idea of a difference quotient, and this is one of the ways that we can write a difference quotient for this particular function f of x. Okay, so the difference quotient ends up calculating the average rate of change on a given interval. Now, if I want to find the instantaneous rate of change at A, what I'm doing is I'm taking this point A plus H on the curve and I'm sliding it along the curve towards the point where the x-coordinate is A. So I'm moving this value this way. So what I'm doing is I'm letting this parameter H get closer and closer to 0. So really that's the only difference between the formula for the average rate of change here and for the instantaneous rate of change, is I'm taking the limit here as H gets closer and closer to 0. And that gives us our formula for the instantaneous rate of change right here. You'll frequently hear this referred to as the limit of the difference quotient. And the limit of the difference quotient gives us the instantaneous rate of change at a point. So this is one way that we can write this, depending on how we label these points on our graph. I'm going to show you a second way that we can label these points on the graph and do the exact same calculations. It's the exact same curve with the exact same points to start. Just a second form of looking at it. Again, we're thinking about the secant line that goes through these 2 points. Only now, instead of labeling this as the point a plus h, comma f of a plus h, this is going to be the point x f of x. And this is still the point a f of a. And so this time when you see the difference quotient, the slope formula gives me f of x minus f of a. That's what you see there, all over x minus a. Okay, different kind of difference quotient. This is still a difference quotient. It's just a different way of writing this particular difference quotient. And then, in order to find the instantaneous rate of change, what we're going to do is we're going to take this x value and we're going to move it closer and closer to a. And so this is going to be the limit as x approaches a of this difference quotient. And so again, we're taking the limit of the difference quotient in order to find the instantaneous rate of change. It's just a different way of writing it. And there are a lot of different ways that we can write this limit of a difference quotient depending on how we opt to label these 2 points. These 2 are by far the most common. I tend to use the first form a vast majority of the time, although as I get older and do more and more problems, sometimes I choose the second form, sometimes I choose the first form. Doesn't really matter. They both can be used. One of them might be easier in one context and the other might be easier in another context. So, it's good for us to know both of these forms and why they exist. I've tried here in this video to really explain to you why these represent the average rate of change and the instantaneous rate of change. So I hope you kind of understand it from there. That's where we're going to end for this video. Come on back next time for the second video in this section where we're going to apply these average rate of change and instantaneous rate of change definitions. All right, see you everybody. Have a good rest of your day, and I'll see you next time.